Hey guys, it's BOOTHDOG here. I have to say, I'm a little concerned today. Boothman's like being kind of weird. I don't know. He's not himself today. Just, I'm a little concerned. Anyway, let's go ahead and start. What are you doing? Hey guys, let's go ahead and get started with today's lesson, and I'll see you after the video. Good morning, happy Thursday. I hope you used your flex day Wednesday wisely. You got some work done, you got caught up on some things, took care of some retakes. Reminder, exit ticket today due by midnight tonight. It will be similar to the last few days. And let's jump into our last notes for Unit 8. So 8.1 was all about types of sequences and how we define them and how we find specific terms of these sequences. 8.2 so far has been about partial sums of arithmetic and geometric sequences, how we express that, how we find like these formulas that let us find these partial sums. But we still have one last learning target here. And it has to do with something called a series. So a sequence, as we know, is an ordered list of numbers. And it just keeps going. A series is that ordered list of numbers, but added together. So a sequence is just our list. A series is a sum. Okay. Now, when it's continued this way, we have ... at the very end, and it just keeps going. Okay, this is known as an infinite series. So let's take a second and think about what that means, because we can pretty easily accept an infinite sequence. It's just this infinitely long list of numbers. Okay, but what does it mean to add together an infinite number of numbers? Now, we start here getting into some interesting concepts about infinity and what this means. Those of you who go on to study further math, you'll learn much more about infinity. There are different types of infinities, different ways that we express it and work with it. But for now, we're really just focusing on this pretty straightforward idea. We're adding together an infinitely long list of numbers. And I'm telling you that given certain geometric series, so if this is a geometric sequence, then adding them all together is known as an infinite geometric series. Given certain geometric series, I'm telling you that this actually adds up to a finite number. Not approximately some number, but it actually equals some number. Now, this is getting into some concepts about infinite sums and what this means that we're going to explore much more in calculus next year. But just to start to get an intuition for it, I really like this diagram, this example. So let's start with a circle. We have one full circle. Okay. Now, suppose I take half the circle. And then to this half, so right now we have half the circle. And then to this half, I'm going to add half of what's left. So what half of what's left? Half of a half. So now I'm adding a fourth. And then I add half of what's left there, 1/8. And then I add half of what's left. And then I add half of what's left. And I just keep adding more and more halves of whatever remains. Now, eventually, as we go to infinity, as I take an infinite number of these halves, what's our total here? Adding all of this together, okay, should make some reasonable sense to us that we end up with one full circle. Now, this is a geometric series. Okay? Our first term is 1/2, and our common ratio, what we're multiplying by to get to our next term, is also 1/2. So this, hopefully, starts to give you a bit of an intuition for where I'm going with this. That For certain types of geometric series, okay, we're adding smaller and smaller numbers. So eventually, as we keep going further and further and further, the numbers we're adding get smaller and smaller and smaller. And so it should start to make some sense to us that eventually, once we get to an infinite number of these terms, we're adding numbers that are pretty much zero, which means that we should be able to add all those other numbers up and end up with some finite term, provided that all of these numbers are small enough that we're not just adding to an infinitely large number. Again, lots of concepts that we'll explore much more in calculus, but for now, this basic idea of a geometric series, it's the only type of series we're going to discuss. If we have an infinite geometric series, so we have a1 plus our second term plus our third term and so on, then this sums to equals, we're going to call this S, and notice there's no subscript here. This is not a partial sum anymore. It's not the nth partial sum. It is just the sum of this entire series. This equals pretty straightforward formula. The first term over 1 minus r. Okay. Pretty simple proof of this. Again, you can ask me about that during our Google Meet. And I also go through this proof briefly when we discuss it in calculus. Now notice that this only works. So this sum, this series, is only equal to this formula when the absolute value of our common ratio is less than 1. In other words, our common ratio is between -1 and 1. Again, that's what we would do if we were dropping the absolute value. So these are equivalent. And that kind of goes back to this idea of, if I'm multiplying by a number to get to my next term, and that number is a fraction, okay, right? That's what this means, that our ratio is a fraction, like fraction less than 1, 1/2 or 1/10 or 2/5 or whatever. That means my terms are constantly getting smaller, right? If I multiply by 1/10 each time, my numbers are going to keep getting smaller. And as we go to infinity, eventually our numbers are going to get so small that they're basically zero. That's what this concept really boils down to. So infinite geometric series is very straightforward. We just have to check, is the absolute value of our common ratio less than 1? If it is, then this is what it equals. Okay. And this formula is on your reference sheet as well. So let's look at an example. Now, conceptually, if you're still not really getting any of this, you're going to be fine just by using the formula, okay, just by going through the process. But especially those of you going on to calculus, I really want you to try to think about conceptually what I'm saying here. So find the sum of the infinite geometric series. Here is our series. Again, it's infinite, it continues forever. Now, an infinite geometric series has a sum, a finite sum, when the absolute value of r is less than 1. So we need to find r here. What is r for this series? What am I multiplying each term by to get to the next? 2 times what is 2/5? 1/5. And we see, does that work again? 2/5 times 1/5 is 2/25. So that continues to work each time. So r equals 1/5. So that means the absolute value of r is less than 1, right? 1/5 is less than 1. So this sum equals the first term over 1 minus r. Our first term of this series is 2 over 1 minus 1/5. And now it's just a matter of simplification. 2 over 1 minus 1/5 is 4/5. Dividing by a fraction means multiplying by its reciprocal. So we get 10/4. which simplifies to 5 over 2. So pretty simple math, but again, conceptually, I'm telling you that this infinite list of numbers adds not close to, but adds to exactly 5 over 2. That's a powerful statement. And calculus is all about making powerful statements just like that. As you can see, I'm very excited. We're finally getting into tastes of calculus. We're really jumping into the pre-calculus part of this course. We really have been all semester. So look forward to that if you're continuing on with me next year or you're going on to calc in college. All right, now the problem we just did is exactly like the types of problems you should expect to see for infinite geometric series on any assessments in this course. This next example that I'm going to do is not really like any problems you'll be tested on, but I really like this problem. It's really interesting. So just follow along, okay? You're not going to be tested on something like this, but it's an interesting application of our infinite geometric series. Find the fraction that represents the rational number 2.3 and then 5.1, and 5.1 have this bar over them. Okay, so what does this mean? What does that bar mean? That's 2.3. That means the 5 and the 1 repeat forever. Now, this is a rational number. A rational number is a number that can be expressed as a fraction, as a ratio. It's kind of difficult, though, to think about how are we going to take this infinitely long decimal and write it as a fraction. Okay. That's not easy to do just off the top of our heads. We're going to turn to our infinite geometric series to do this. Now, let's take a step back here. 2.3, how would we express that as a fraction? Okay. 2.3, I know how we feel about fractions. 2.3, well, that's 23 over 10. Okay, right? We have, if we're writing this in tenths, 3 is in the tenths place. We have 3 tenths plus 2 wholes, so 20 over 10 plus 3 over 10 is 23 over 10. What about this 51 here? This is in the thousandths place, so this is 51 thousandths. And then this next 51 is in the hundred thousandths place. And the next 51, we add another 2 zeros. And we can keep doing this. And it would just continue. So in some sense, okay, we could write out this infinite series of numbers, this infinite series of fractions, and when we add all of this together, this should give us this decimal, right? That's what each piece equals. So we're adding them all together. We're going to get this decimal back. Now, this part right here, from here over, is infinite. And to go from one term to the next, we're multiplying by 1 over 100. Our first term is 51 over 1,000. Right, again, I'm starting here. And since the absolute value of r is less than 1 for this infinite geometric series, this whole infinite series sums to 51 over 1,000 all over 1 minus 1 over 100. And we simplify this. We get 51 over 990. And so this 2.351 repeating is 23 over 10, plus we just showed that the rest of this decimal sums to 51 over 990. getting a common denominator and adding these together and simplifying gives us 388 over 165. And we can always check. We plug this into a calculator, we try to divide this by hand, we will end up with the decimal 2.351 repeating. So this is how we take these really weird decimals and turn them back into rational numbers. Of course, not every decimal is a rational number, but many are. And this is how we do it. So a very interesting application of infinite geometric series. Again, this isn't the type of problem you will ever be asked in this course, so don't worry too much about that. But again, I just think it's interesting. So tomorrow we are going to practice 8.2 and we'll take our exit ticket. Today you do have that exit ticket due by midnight tonight, and I encourage you to work through the 8.2 independent practice problems. Next week, looking ahead, on Monday we will review this unit, so we really only had 8.1 and 8.2, and then we'll take this unit exam on Tuesday. And then we'll move on to our final unit of the year, Unit 9, very short, but incredibly important, moving on to calculus. Let me know if you have any questions, otherwise I'll see you tomorrow. Hey guys, it's Boothman. I'm sick of BOOTHDOG starting and ending every single one of these videos, so today I kind of pushed him out of the way. It was great being able to teach you guys today. I look forward to tomorrow. Do your exit tickets. Stay safe. Join our Google Meet if you have questions.